Hello, this is Dr. Joe Trout from the physics program at the Richard Stockton College of New Jersey. In this presentation, we're going to discuss Chapter 1, which is on monitoring the weather. Chapter 1 gives us an overview of all the topics that we're going to discuss during this course. So we'll introduce them here and discuss them in detail as we go through the course. So the driving question in this chapter is, what are some of the basic characteristics of the atmosphere and weather? And once again, we'll introduce the topics that we'll discuss this semester and some of the tools and basics understandings that will help you investigate the atmosphere. The first thing we should do is discuss the difference between weather and climate. Weather is the particular state of the atmosphere at some distinct place and time. So for instance, we could talk about the weather right now in Galloway, New Jersey. Or we could talk about the weather in Philadelphia next Tuesday. When we describe the atmosphere and weather, we usually use variables such as temperature, humidity, cloudiness, precipitation, which is rain or snow or sleet or hail, wind speed, and wind direction. Meteorology is actually the study of the atmosphere and the processes that cause the weather. When we talk about climate, we're talking about the weather conditions at some locality averaged over a specific period of time. In the United States, we use 30-year averages, and we update it every decade. So the climate is the average of the weather. So for instance, we'll average the temperature every February 1st for the last 30 years, and that gives us some idea of the climate. And we'll do this for every day. Actually, we'll do this for every hour of every day. So when we talk about climate, we're talking about the average weather in some location. Climate also includes weather extremes. So for instance, extreme droughts or floods. This is also part of the climate. Nowadays, we have tons of information out there about the weather, right? You can go on the television and watch the Weather Channel or the local newscasts, and they do quite well. We have NOAA Weather Radio that has continuous broadcasts repeated every 4 to 6 minutes. These are interrupted with warnings and watches, so for instance, hurricane watches or flash flood warnings. And we also have the internet. So for instance, if you're planning on going to the beach today, the first thing you do when you wake up is probably open up the internet and go to your favorite weather website and find out what the weather will be like today. We can also look at radar and satellite images for a particular place at any instant of the day. When we look at these weather systems, or when we get the information from the TV or the radio or the internet, we usually have weather maps, which include national and regional weather maps. We also get satellite and radar images, and we can look for data on current and past conditions. So for instance, we can look at, if we're going to plan a vacation, we could go and look at what the weather normally is for the week we're going at any place in the world. This won't tell us what the weather will be like on our vacation, but it will tell us roughly what kind of clothes we should pack. We have short-term weather forecasts, which are 24 to 48 hours. And these are usually pretty reliable. We also have long-term forecasts, which go up to 7 days or even longer, And these forecasts are not as reliable and usually have to change as the time progresses. What you see pictured here is an automated surface observing system. And what that'll give us is the temperature, wind direction, wind speed, humidity, and precipitation at the surface of the Earth. Normally you'll hear people talking about high pressure and low pressure systems if you watch the Weather Channel or you listen to the TV news. High pressure systems are called anticyclones and low pressure systems are called cyclones. You probably know that if you have a high pressure and a low pressure, air or gas will move from the high pressure to the low pressure. So for instance, let's say you have a scuba tank and you compress air inside the scuba tank and it's under a very high pressure. It's much higher than atmospheric pressure. So what happens when we open the valve? Air rushes out from the high pressure to the low pressure. Right, it would be kind of scary if you had a full scuba tank and you opened the valve and all of a sudden it started sucking in air, right? Doesn't make any sense. So this is really important to weather. So we'll watch these high pressure and low pressure systems and find out what happens. So in the northern hemisphere, if we have a low pressure system, what happens is air rushes in at the surface and it also rotates around the low pressure system. So for instance, we see a symbol here, an L. Air rushes into it and around it in a counterclockwise direction. If we have a high pressure system, air rushes out of it and it rotates in a clockwise direction. And once again, these high pressure systems are called anticyclones and the low pressure systems are called cyclones. Also shown on this map are these lines that represent fronts, and we'll talk about that in a little while. Here, this ones with the blue triangles are supposed to represent the biting cold north wind. And what this is a cold front. And the air behind it is cold, and the air in front of it is less cold or warmer. And what happens is the cold air pushes through and overtakes and pushes the warm air out of the way. The red lines with the little suns on them are warm fronts. And what happens here is we have warm air back in this direction. The front moves up towards Canada and brings warm air into Canada. We also see that it also shows the precipitation, and these dots here are rain. It must be colder over here because what we have is snow. And down along this cold front, you see we have thunderstorms that are formed. So these high and lows refer to air pressure. And we'll talk about pressure later in this course. But pressure is force per area. And what it has to do is the weight of the air above us is pushing down on us. And that's what's providing the pressure. When we say high pressure, we mean high relative to the surrounding air. And low pressure is low relative to the surrounding air. Normally we're happy when a high pressure system moves in because what it brings is fair weather. We see there's a clockwise rotation of sinking air. This is in the northern hemisphere. And they generally track from towards the east and southeast. Whenever you talk about a low, so a lot of times if you hear them talk about hurricanes, they keep talking about this low and it's getting deeper and deeper and deeper. Lows usually bring stormy weather. They have a counterclockwise and rotation of rising air in the northern hemisphere. And they generally track towards the east and northeast. If we have lows tracking across the North United States and southern Canada, they produce less moisture than lows tracking across the southern United States. Weather to the west and north is usually cold, and weather to the south and east is usually warm. So for high pressure, we have fair weather coming in, and for low pressure, we have stormy weather coming in. And as we go through the course, we'll explain why this happens. The pressure is usually measured in millibars. That's what the MB stands for here. And what you see is here's the high pressure. It's at about 1,024 millibars. And it's going out to 1,012 millibars. So here's the high pressure. Here's the low pressure. So the air would blow out from the high pressure. The reason it rotates, we'll find out, is due to the fact that the Earth is rotating. And this is due to the Coriolis effect. We also see a low labeled here. And these lines where the pressure are marked are called isobars. And what happens is, once again, we see here the low pressure is in the center at about 992, and the high pressure is on the outside at about 1,008. So the air is going to blow from the high pressure to the low pressure. Once again, it rotates, and this is due to the Coriolis effect, which is due to the Earth's rotation. This semester we'll talk a lot about air masses. And these are huge volumes of air that cover thousands of square kilometers. A kilometer is a unit of length. And many of you have probably ran a 5-kilometer race and know that 5 kilometers is approximately 3.1 miles. These air masses sit in a particular spot for a long time, and what happens is they take up the characteristics of that area. So for instance, if we have an air mass that's sitting over the desert, it's going to become hot and dry. The temperature and humidity is going to be constant through this air mass. If it's sitting over the ocean near the equator, it's going to be hot and wet. These air masses don't stay in one place forever. They start to move, and this is what produces our fronts. And the front is just the transition zone where we go from one air mass to another air mass. We'll talk about this in detail in about 5 chapters. So these air masses gather the characteristics from its source region. So for instance, we get cold, dry air masses form over higher altitudes over the land, over the continents. Cold, humid air masses form in high latitudes over oceans and other maritime surfaces. Warm, dry air masses form over the continents near the equator, and warm, humid air masses form over the water near the equator. These fronts are the transition zone between these air masses. So for example, we have a cold front. Cold fronts are usually pretty dramatic. What happens is the cold air comes crashing in, and the cold air has a higher density than the warm air. And it comes crashing in and pushes the warm, moist air up into the atmosphere, where a cloud forms and we get strong storms. Warm fronts are usually much more mild. So what happens is the cold air retreats and the warm air filters in. So in the summertime, a cold front will come through and bring violent thunderstorms. A warm front will come in and bring gentle, steady rains. We name these air masses according to the regions they come from. So for instance, we have polar air masses are colder in the winter and milder in the summer. Tropical air masses have less seasonal variation. They're usually warm and wet. Air masses start to modify as they move from their source region. So then they move into another area and they take over they begin to have the characteristics from that area. The transition zones between these air masses are called fronts. And where the fronts intersect the Earth's surface is known as where we draw the front symbol on the map. So the fronts are three-dimensional and they slope over the cold air. With warm front clouds and precipitation occur over a wide band, and they may occur for 1 to 2 days as it comes through, and it's usually light precipitation. Cold front clouds and precipitation occur over a narrow band, and they may happen in a few minutes to hours. So I'm sure living in the Northeast near the coast, you're familiar with cold fronts coming through and you'd have a violent thunderstorm that might just last a few minutes. And there may be very heavy precipitation if there's moisture available. When we look at these fronts, the wind direction can actually be different on the two sides of the front. So for instance, if we have a cold front coming in, that cold air may be coming down from Canada. When we talk about the wind, we usually talk about the direction where it came from. So for instance, in our area, a north wind comes from Canada, and a southerly wind comes from the equator. The reason we describe it that way is because we're more interested in where the air came from than where it's going. If you tell me a north wind, I expect possibly cold and dry air. If you tell me a southern wind, I expect a warm and possibly moist air. So, if we have a cold front that cuts through New Jersey and it's oriented in a north-south direction, what we'll normally see is that before the cold front, we'll have a southerly wind. And after the cold front, we'll have a northerly wind. So the wind direction on either side of the front can be different. Some fronts have no clouds or precipitation, so I'm sure you've seen this winter a cold front move through which had no clouds and no precipitation, just a change in temperature. Clouds aren't going to form if there's no moisture available in the atmosphere. In the summertime, we actually see that the temperatures on both sides of a cold front might be the same temperature. And it's actually a difference in humidity that tells us that there's two different air masses there. We still call it a cold front. Fronts are usually anchored to lows on the weather map. So if you look at a weather map, you usually see that somewhere at the end of the front, you'll see a low symbol, and that's where the front is anchored. When we have thunderstorms and severe weather, they often occur in warm, humid air masses located between the cold and the warm front. So if we look at coastal areas, we see that lake and sea breezes may lower summer temperatures, and we'll talk about how come you feel a nice cool breeze coming off the ocean when you're sitting on the beach. These may push 10 to 50 kilometers, which is 6 to 30 miles inland from the coast and shore. So don't forget, you people who run, right? 5 kilometers is about 3 miles. So 10 kilometers is about 6 miles. So if we have 50 kilometers, that comes out to be about 30 miles. We also have things like heavy lake effect snows on the Great Lakes, and these occur in late fall and winter. In the central U.S., is the most common location for tornadoes in the spring. Thunderstorms are very common in Florida, and if you've lived in Florida for a while, what you'll see is that there's usually a thunderstorm at almost every afternoon during the summer season. We also get tropical storms and hurricanes that impact the Atlantic and Gulf coasts, mostly August through October, and they're very rare on the West Coast. So when we get to chapter 13, I believe, we'll talk about hurricanes and how they form and how to protect yourself if one does hit. So when we make forecasts about the weather, what do we like to tell you? We usually like to talk about the maximum temperature, which usually occurs in the early to mid-afternoon, and the minimum temperature, which occurs around sunrise. Because what's happening is that while the sun wasn't shining on the spot of the earth that you're located, the earth cools. And it keeps cooling all night, and then as soon as the sun comes up, it starts to warm up. So normally you'll have a minimum temperature that occurs right around sunrise. We also like to predict the dew point. This is the temperature at which air must be cooled at a constant pressure for dew to form. In a few chapters, we'll talk about the dew point and what it has to do, how dew forms, and what this has to do with things like clouds and storms. We also like to talk about the relative humidity. The relative humidity talks about how much moisture is in the atmosphere as compared to how much moisture the atmosphere can hold. This has something to do with temperature. So you may notice that in New Jersey, in the winter, the atmosphere is usually very dry. So when the air is cold, it's harder for it to contain moisture. On the other hand, in the summer, we get some really humid days. So we see is that it's easier for the atmosphere to contain moisture if the temperature is high. So for instance, if we have 100% humidity in the winter and 100% humidity in the summer, there is much more moisture in the atmosphere during the summer. The reason that they're both is 100% is that the relative humidity compares the amount of moisture in the atmosphere to the amount of moisture the atmosphere can hold. We also like to predict precipitation amounts. So what we find is that a general rule is 10 inches of snow equals about 1 inch of precipitation. So if you have 1 inch of rain and you freeze it into snow, it expands to about 10 inches. We also like to we also like to predict air pressure and its tendency, whether it's rising or falling. If it's falling, we expect a storm to come through. If it's rising, we expect clearing and calm mild weather. We want to predict wind direction and wind speed, and also sky cover. So how many clouds we have in the air. We also like to predict weather watches, and they're issued when there's hazardous weather is considered possible. And weather warnings, that's issued when hazardous weather is imminent or actually taking place. So for instance, we'll have flood watches and flood warnings. And first we put out a flood watch. That means it's possible there's going to be a flood. And then just before the flood hits, put out a flood warning. How do we make these predictions? Well, one thing we do is look at the atmosphere's condition at the moment. Right, so what does the atmosphere look like right now? So we use satellite images. So the first is a geostationary. This is a high orbit, about 36,000 kilometers, or about 22,000 miles up from the Earth's surface. And it orbits exactly the same rate as the Earth's rotation. So that's why it's called geostationary, because it sits at the exact same spot around the Earth, because it's rotating at the same time the Earth is. There's currently 2 of these, and they provide a complete view of much of North America and the adjacent oceans to a latitude of about 60 degrees. They're positioned over the equator at 75 degrees west longitude and 135 degrees west longitude. We also have polar orbiting. So these are lower orbits, about 500 to 600 miles. And they provide overlapping north and south strips of images. And it passes over the same point twice every 24 hours. So here's a picture of a geostationary. So it stays above the exact same point at the equator as the Earth is rotating. The polar orbiting satellites move through the North and South Pole, and they sweep through across the globe, and we come up with pictures that are swatches of a portion of the globe. One type of image these satellites send back are called visible. These are black and white photographs of the planet. The bad thing about visible imagery is that it's only available during the daylight hours. So what happens is we look for highly reflective surfaces and they appear as bright white, and less reflective surfaces appear darker. So clouds reflect very well. So the sunlight comes in and reflects off the clouds, and we can see them using a camera. There's also infrared. And if you look at the difference between the visible and the infrared, what you'll notice is that the visible, there's a lot more detail and a lot more contrast in there. The infrared images are kind of washed out. So if you look, this is the visible and the infrared for the same day, the 24th of November in 2008. And here's the visible, nice crisp picture where you can see details of the clouds. Here's the infrared, And the clouds are a little bit washed out. They don't look as sharp and crisp as the visible image. The good thing about infrared is that it's available anytime. So even when the sun sets on the United States, we can still get images of what the clouds are looking at or look like. What it actually is showing you is a temperature comparisons of features within an image. That's why it's infrared. Infrared is heat on the electromagnetic spectrum. Here the white equals colder. But the higher cloud tops appear whiter because they are colder, and that's what we're looking at here. We also get water vapor imagery. So we can actually track the water vapor and see where it's coming from. So shades of white show increasing moisture. Upper level clouds appear milky to bright white. So we can track how the moisture is entering into the atmosphere and where the moisture is going. Not surprisingly, a lot of the moisture is coming from the ocean and not from the continent. We also have weather radar. And a fairly recent development is called Doppler radar, which can detect the movements. We'll talk about this in chapters to come in detail, but in essence, what a Doppler radar does is send out a signal, and it reflects off of something, and it comes back. We know how fast the signal was moving, and we record the time it takes to return, and from that, we can figure out how far away it is. So for instance, if you're driving 60 miles an hour down the parkway, and let's say you're driving 60 miles south down the parkway, and you drive for 2 hours, you'll be 120 miles away. If you drive 60 miles an hour for 3 hours, you'll be 180 miles away. So that's in essence is how these work. So I'm sure most of you have been to the mountains sometime, and you yelled over the edge of a mountain and waited for the echo to come back. Well, that's exactly how this works. Only instead of using sound, we're using microwaves. A lot of times combinations of images, such as a composite image of an infrared and a radar, can give you a lot of information. And you can determine a lot about the weather by watching the clouds, by watching the sky. So clouds are actually aggregates of tiny water droplets or ice crystals or a combination of both. So what it is a bunch of water droplets just floating around in the atmosphere. A cloud that's in contact with the ground is called fog. So soon we'll talk about clouds in a lot more detail, but as I said, this first chapter is just giving you a brief overview of the things we'll talk about. So if we look at the cloud forms, there's stratiform, which are sheet-like clouds formed in horizontal layers. We have cumuliform clouds, which are puffy and like cotton balls. We also have the appearance of high, wispy, feather-like clouds composed of ice crystals. In the western sky is often the first sign of an approaching warm front. So if we look at these clouds, we can tell what weather is coming towards us. Here's a picture of cirrus clouds, and they appear fibrous because they're composed mostly of tiny ice crystals. Here we have a picture of some relatively low clouds, and they're composed of tiny water droplets, and they have much more defined edges than these ice crystal clouds. And once again, if we have a cloud that's touching the atmosphere, that's touching the surface, we call that fog. We also have fair weather cumulus clouds pictured here, and these are most common during the warmest part of the day and then vaporize after sunset. Then we have clouds with vertical development. So shown here, we see cumulonimbus clouds, and nimbus is a prefix meaning rain producing. And what we see is that these have very large vertical extent, so they go very high up into the atmosphere. And these clouds always produce lightning and sometimes heavy rain, hail, snow, strong and gusty surface winds. What we'll find out in several chapters is that the clouds can move in different directions at different altitudes. So as we move up into the atmosphere, what we can see is that wind will blow in different directions. And we're going to learn out why that happens and why it's important to the weather. So that ends today's lecture.